Yes, everybody's saying yes. So today it's a pleasure to introduce Professor Gianluca Iaccarino. He's a professor of mechanical engineering at the Stanford University. He's also the director of the Institute for Computational Mathematical Engineering. So, he got his PhD in Polytechnical di Bari in 2005, and then he worked for some time in the Center for Turbulence Research at the Stanford. And finally, he joined as a faculty in 2007. So I'm also very happy to have Iaccarino here. So I know him from some time, in my times when I was at the Stanford. I think that he does a very interesting research. So I hope that you all enjoy the presentation about some logistics. So usually in the virtual format, so what we'll do is so Iaccarino will go through the presentation. We are going to try to keep the questions at the end. So at the end, you can just unmute yourself and raise your hand, and then I'll give you, I will check who is in first in order, so you can speak, or you can just write your question in the chat. And with any further ado, just Iaccarino, go ahead.
Thank you very much, Adrian. Thank you for the invitation, and welcome everybody. I'm going to give an overview of a large program at Stanford as part of this advanced simulation and computing program. So this is not the title of just my talk, but is, as we will see in a moment, a large program in the United States. The part that I'm going to focus on the other end is obviously the work that we've done at Stanford over the last several years. And just to orient you or give you a little bit of a context of simulation and computing at Stanford, I want to focus on one particular area, which is simulations of turbulence that have been pioneered at Stanford actually quite a long time ago, in the 70s and the 80s. This is one of the more spectacular simulations that were run at the end of the 70s. The visualization that you see is actually a numerical simulation of a turbulent flow within two flat plates. It's called channel flow. And these visualizations are intended to actually reproduce a specific experimental setting. In this simulation presented at APS in 1980, the authors, Steve Moyne and Moser, really were trying to establish the fact that you can use numerical simulation to do exactly what you can do in experiments in a way that is very, very effective. Now, two elements, I won't talk too much about the physics and the specifics of this simulation, but two elements are kind of interesting. One is that you see this visualization is relatively choppy, and the reason for that is because at the time, what they had to do to create this movie was actually take snapshots of a computer screen and then mount them together as a movie. So this is actually a work of art in addition to a great work of physics simulation. The other element that I think is critical and is sort of the common theme of all the projects that I'll mention in this sort of historical review as a start of the presentation is the picture on the left, which is the supercomputer that was used at the time to perform this simulation. It was, again, obviously old supercomputer by any standard today. But it was already a parallel computer. It was able to do more, than 10 megaflops. You must be familiar with the idea, the concept of flop, floating point operation per second, which is sort of a way to measure performance. And it was an extremely large and extremely user-unfriendly computer. So this was really a challenge even to just connect the idea of the mathematical modeling to these computing sources. But this was one of the challenges that I had to work out. Now, I'll move quickly from the 80s to sort of the start of the ASCI program, this Advanced Simulation and Computing Program, which is a project that started from the Department of Energy and funded multiple universities for many, many years. At Stanford, we worked on a large-scale project that involved simulations of a jet engine. In this case, you're seeing now a visualization of a turbulent flow in a combustor, in a jet engine combustor. The key feature of this project is, once again, the fact that you have a very complex flow, but more importantly, you have challenging in performing this simulation on the largest supercomputer that was available at the time. In this case, the ASCI White supercomputer that was becoming or made available to the project around 2002, 2003. And this project, this computer now has a massive amount of compute resources, 4,000 CPUs, and reaches 5 teraflops. So in a sense, we have enormous amount of resources compared to the previous simulation I was showing. But the one thing that was interesting about the project and the timing of the project is that at the time, it wasn't completely clear that you could actually use such a large resource to perform one massive calculation of a complex industrial engineering problem. And so the whole idea of the project that lasted actually 10 years at Stanford was to demonstrate that you could do this kind of simulations. Now, quickly after this project or towards the tail end of this project, it was clear that we could actually perform simulation of this kind. The question was, is there any physical or engineering insight that you can extract? Are these simulations actually credible? And so the ASCI program started to move from the idea of demonstrating that you can do the simulation to the idea of understanding the predictive quality of this simulation. And so the project that we started in 2008, and they're still continuing today, are called PSAP projects. PSAP stands for Predictive Science Academic Alliance Program. So predictive is the keyword in this setting. And the simulations now moved into more complex realm. In this case, you're seeing the first of the PSAP program at Stanford. That was the simulation of an hypersonic combustion system, so a scramjet engine. On the left, you see again the sort of computational resources that were made available at the time. Titan was the top supercomputer in the world at the time. It reached, and the interesting sort of technological advance was that it was the first computer to have accelerators, GPUs in this case. And the key element, though, is the speed that these computers, the top performance measure that is reported there, petaflops. So we reached petaflops around 2011. And the thing that is interesting about sort of this sort of progression of projects and activities, the fact that every 6-7 years, you have a 3 order of magnitude increase in compute performance. So the amount of simulations and the speed of compute actually as this sort of continuous growth that is reflected both in the compute resources that you have, but also in the type of simulation complexity that we have been focusing on. The project that I'll spend more time today talk about is actually this project that ended now a year after, a couple of years ago, and that had to do with the simulation of a solar receiver, so a solar energy harvesting device. I'll tell you more about it in a moment. But again, one component that remains constant across these sort of 20+ years is the access and the need to compute on sort of the newest available compute resources. In this case, Summit was the machine that became available shortly before the start of the project. And this is a 200 petaflop machine. So again, about 3 order of magnitude increase in compute performance. And then finally, the project we're working on right now, and I'll just say a few words of it at the end of this presentation, is a project that is devoted to the predictive ability or the ability to predict reliability of a ignition system for a rocket propulsion system. So in this case, again, the complexity of the physical picture has to do with turbulence as a key driver, but a lot of other component that have to do with, obviously combustion, the ignition process, and so on. And once again, we're lucky enough in this project to sort of have access to this sort of increasingly more powerful computer, and we are actually getting ready and prepared to run on the new exascale machines that the Department of Energy is putting together, and Frontier is one of the most interesting sort of set of hardware system that we will compute on. So this sort of a big 20-year development really is started with the Department of Energy is sort of establishing this advanced simulation and computing program. As I mentioned, is a program that funds universities through these 5 years project. But the most important, or the other important element of this project is that is a very, very large commitment by the Department of Energy. It funds a lot of activities also internally in the national labs, but also it has funding directly to support the development and then the establishment of these supercomputers. So this supercomputer summit and frontier that I just mentioned are actually part of the same project. The budget and the funding comes from the same project, which means that simulations and computing are really coming together. The simulation on one end to address a specific project, and the computing resources on the other to sort of enable those simulations to occur. So what are the key elements that relate these projects? Why we are solving, or we are tackling a project that has to do with propulsion, then energy harvesting, rocket systems. What are the elements that sort of make this project sort of follow one after the other? The character of this project are reported here. These sort of 4 key elements. The first is to have actually an overarching scientific challenge. So these projects really have at the sort of inception a sort of a focus on technology that cannot really be reliably simulated with today's technology. So limitations that have to do with either a scientific question that is not well understood or the complexity of the system that are not well studied or well available. The second very important is the multiphysics. So all these projects involve turbulence, as I mentioned before, but turbulence plus something else. So first, turbulence plus combustion, plus radiation, particle transport, and the coupling between these different elements, these different physical processes, is very important because it poses challenges in the way simulations are actually conducted. And so this is a key element. Obviously, I already mentioned high performance computing as a key driver. So all these projects have at their sort of core the need to perform simulation at the extreme scale, sort of whatever resources available because of the complexity that is involved. And then the idea of predictive simulation, the idea of predictions with confidence. So not just a prediction that has sort of a general agreement with some experimental observation and so on, but some rigorous assessment of what are the remaining uncertainties of simulations. So we'll see all these elements as we move forward. My intention for the remaining of the talk is to sort of give you a sense of this project, sort of the solar receiver activity that we did, but then focus on these 2 elements, on the uncertainty side and the computing element. And then just to finish, I'll say a few more words about the new project that we're working on right now. So let me start with the multiphysics simulation. Sort of this project, the core sort of idea is understanding the mechanism of harvesting solar energy in the system. You might be familiar with solar energy devices based on photovoltaic cells. This is a completely different system. In this case, what you're seeing actually in this facility in New Mexico is a field of mirrors. So this is a very large, relatively large field of mirrors that all concentrate. They're all concentrating solar light onto a target, which is on this tower, basically. So this is a device in which the energy is now concentrated over a target. If I flip the tower itself, you see that there is a target there is about 1 meter diameter. And that target now illuminating the tower is actually a very, very highly concentrated radiation flux that is impinging on that surface. So the question is now how to transfer that amount of energy to a fluid that can be used for a thermodynamic cycle, right? So you have that energy available now. You want to transfer it to something that allows to use it mechanically through a thermodynamic cycle. So the system that the folks at Sandia have developed is actually a little bit different in the sense that instead of transferring it directly to a fluid, they are actually storing the energy. So this is a storage energy storage system. So the storage medium are solid particles that are dropped in a curtain within this tower. They are exposed to these extremely high concentrated heat flux, and then they obviously become increase their temperature, increase the internal energy, and then this energy is stored in the system. And then at a later stage, when you want to actually use the energy for some mechanical use, then you just by convection you pass a fluid over this storage system and extract the energy by convection from the particles themselves. So our goal was to think of a different system where the storage actually does not occur and the energy is transferred directly to a fluid. And so the basic idea is that particles are much smaller. The system is actually driven by a turbulent fluid moving through the system. It's actually air in this case, so it's transparent to radiation. But the particles are much smaller. They absorb radiation by passing through that target, heated target. And then they distribute the heat directly, or they release the heat directly to the fluid because of the smaller size. And the question now is how to optimize and what kind of system do we obtain in this case. One of the challenges that we already know that when particles are present in a turbulent flow, when this is an airflow laden with particles, we already know that there is a relatively complex interaction. Now the question is what the interaction is when you have radiation that also plays a role. Now, before moving to show you some ideas about what this problem entails, I just want to mention again the idea of multiphysics and why this creates a simulation challenge. So without going in details of the equation, the challenge that we have is that to simulate turbulence, you typically use a Aurorian framework. So you solve PDEs on a grid, the Navier-Stokes equation on a grid. To transport particles, the most effective way of doing it, at least in this regime, where the particles are dilute or the multiphase flow is dilute in terms of amount of particles per unit volume. Basically, the preferred approach is to use a Lagrangian approach. So you transport the particle through Lagrangian means within this flow field. And then you have to capture radiation. So radiation in this case is best captured either through Monte Carlo ray tracing or through a discrete ordinate type method. And so these three phases, or these three physical processes, require actually quite different numerics, and the coupling between them is what makes the problem really challenging. And so from the point of view of stressing sort of multiphysics, this is one of the key aspects of the problem, that we cannot take shortcuts and try to simplify the problem so that we can get high performance computing capabilities out of this problem. We have to use the methods that are best suited for each one of the phases of the processes, and then build a coupling mechanism that still preserves effectiveness of the simulations. Now, from a physics perspective, one thing that was clear from the beginning in the project is that without radiation in a particle-laden turbulent flow, we expect turbulence to decay. So the particles are extracting energy basically from the turbulent structures, and as a sort of a general sort of framework, we do expect turbulence to decay. Now the basic idea of this project though is that we want turbulence to be active because we want turbulence to interact with the particle phase, and actually we want to operate in a regime where the particles are preferentially concentrated. So turbulence actually leads to particles, or to particle dynamics that can be very effective in concentrating, clustering particles in specific areas. If that happens, we do expect radiation absorption to be very high and locally. And that idea of local heat transfer is really useful to sort of enhance sort of the absorption and then effectively lead to higher temperature in the fluid. And so the first complexity is that whenever we have radiation, the question is that if we can sustain turbulence, because if we lose the turbulence, then we have basically a completely different regime of operation. And it turns out that the coupling is actually quite complicated. When you have particle-laden turbulence, there's only a transfer of momentum and effectively kinetic energy between the two phases, the air fluid phase and the particle phase. But in general, when we have radiation, especially in this setting where the fluid is transparent, it's air in this case, the complexity is actually quite a bit increased, especially because there is sort of this counter transfer of energy from the particles that are absorbing to the fluid that effectively is the final goal and specific. Now, we performed simulation at the beginning that actually demonstrated that this coupling is actually effective in maintaining turbulence. So what you're seeing in this simulation, these are idealized, turbulent boxes. These are really simple, simplified cases. But what you're seeing is in the right-hand picture here, the particle concentration, is that the system starts with the turbulent flow fully developed and an homogeneous distribution of particles. But because of the conditions, very quickly particles get concentrated. So you see these sort of purple regions that are regions of very, very high concentration compared to the yellow sort of initial concentration. And in correspondently to those high clusters of particles, we also see a very large energy and temperature increase. These turbulent waves that are generated in this energy transfer actually introduces additional mixing and keeps turbulence basically alive and healthy. And as you can see from the temporal distribution of the turbulent kinetic energy in this box. So the idea is that in a specific range of conditions, we can actually transfer the energy, so absorb the energy, transfer it to a fluid, but also keep the energy in the turbulent flow sort of alive without really having this decay. And this is valuable because the system that we're working with is actually a system that is forcing sort of the flow because we want to achieve high mass flow rates to get an efficient thermodynamic cycle output. So the end result is that we do have a mechanism now we can study that has sort of now looks very much like the real system. Is actually reproduced in a laboratory. So the laboratory is a vertical tunnel where you have a sort of a duct that will sort of look like the tower that I was showing you before, that is exposed to radiation. Radiation in this case is imposed through laser diodes. Is a control lab apparatus. And we can do simulations that are exactly the same. In this case, you're seeing a simulation of a turbulent flow in that duct. Is exposed to radiation on one side. So radiation comes from in the simulation from the bottom to top. So it is on the side that the temperature increase. And the one thing that you see in this visualization as well is that we are showing the temperature increase in the fluid, which is sort of, again, from left to right, from the entrance when the fluid is cold, all the way to the right when it's exposed to radiation. But as I said, the fluid is transparent, but the radiation is only absorbed through the particles. And I'm showing particles only in a particular section, but in reality, you have to imagine that the entire duct is filled with very, very small particles. So obviously one question is if these simulations are predictive. And the idea here, again, is to compare to experiments in the lab. And you see some comparisons below without going in detail. The one on the left is the most important one, which shows actually the fluid temperature at the exit of this duct compared to the fluid temperature at the entrance. So this is effectively how much energy has been transferred to the system. And it's showing here with the different amount of particles in the system. So the different colors have to do with different amount of particles. And you see that there is a relatively good agreement, but also some remaining discrepancies. And this is where I guess the challenge becomes in terms of these simulations are basically the best we can do at this point. The question is to try to understand why there are remaining discrepancies. And the truth is that simulations and experiments are not exactly the same. The differences are partly due to assumptions that we make and partly due to other contingencies that are present in the experiments and they're not necessarily reproduced in the simulation. So for example, one very real source of uncertainty these days is the fact that in a real world scenario, we need to actually manufacture the particles that are used in the lab apparatus. And then these particles are sort of dropped into the vertical tunnel. the particles, although nominally are designed to be 11 micron particles, are manufactured in a way that cannot really preserve that size exactly. And so we have a distribution of particles that we actually are considering the experiment, and the probability distribution of that particle size is actually reported here as an example. And in this case, you see that we can actually perform simulation both by using the design conditions and use the real particles. And you see that in terms of temperature distribution in a specific setting, like I'm showing you here, you see that there are actually quite a bit of qualitative and quantitative differences. And so this is one source of difference in the experiments and simulation that can actually be addressed and eliminated. And there are many more. For example, the source, the radiation source is not an ideal radiation source. It's again a real laser diode that is emitting at a certain frequency in a certain spectrum or with a certain spatial distribution that again you can directly capture in your simulations. And so you can, with some attention, eliminate some of the differences between what you originally designed to be your system and what is actually the system that is in practice realized. But more in general, this sort of points to the fact that we need to be careful about what is uncertain in the simulation or what is actually different in a computational setting versus an experiment. And this is where uncertainty sort of come as a primary element to this project. We distinguish typically uncertainties that are occurring naturally or in some sense are present in the real system that we want to analyze. And so I mentioned already particle sizes. And just to give you, again, a bit of a direct assessment of that, the picture you see on the top here is actually the powder that is used in the experiment. So these are the actual particles, millions and millions of particles. At the microscope, this is how they look like, the picture in the bottom. And you see that they are definitely not 11 micron, and they're also not very, very spherical, which is another assumption we typically make in Lagrangian modeling. And just to sort of be a little bit careful with the evidence that is provided to you, the issue is that the manufacturer cannot really provide you a very, very precise or much more precise set of particles, but this is the actual bottle that we received from the manufacturer. And you can see that on top of the bottle itself, there is a probability distribution of the actual particle sizes. So it's not that this idea that the particles are not 11 micron was hidden. It was very explicit from the beginning. And so ignoring it is actually would be a real problem. So in this case, we are adopting actually a distribution directly in a simulation, and this is one of the elements that you can do, one of the activities you can do to actually try to reduce the uncertainties. It turns out it's not the only uncertainties, there are many others, and many of these uncertainties are introduced by our own modeling assumptions. And so in that sense, it's critical to consider those modeling assumptions and understanding how much evidence there is. For example, for collisions between particles, it's clear that we need to accommodate sort of a physical law that represents the process of collision that is actually quite complex, especially when you have particles that are not necessarily spherical, that have different sizes and so on and so forth. And so it turns out that these are some of the main uncertainties we have to consider. So how to proceed then to compute in this case? So the first step, as I said, is to identify the uncertainty. So being very explicit about the potential sources of uncertainty. Then what you do is that you collect the evidence that is available, and in some sense, you build a model or a representation for the uncertainties. In our case, at the end of the project, we realized that after many, many iterations, these 14 are the actual major sources of uncertainty or critical sources of uncertainty in our system. And as you can see, they are related, without going in details, they're related to particle restitution coefficients that have to do with actual collision and interaction between particles and the wall. Some of them are related to the radiation, both in terms of the radiation input and perhaps losses that are in the system, but also the characteristics of the particle, the absorption coefficient and the scattering coefficient of the particles. These are all elements that are all parameters, all coefficients in the simulations that need to be specified precisely. But on the other hand, the evidence only gives us some rough information about what these values are. And so in this situation, what you do in a very simplistic way is that you basically take these inputs as parametric inputs, and you select basically realization. So you pick values within all these intervals. For each one of these 14 variables, you perform, or the values of these 14 variables, you perform simulations. So you run an ensemble simulation. And then out of that, you can build confidence interval, statistical confidence interval. And this is sort of the process that we have used to build the simulations that I showed you. Now, one thing to keep in mind is that if you simply do this through an ensemble of the simulation, you very quickly run out of compute power. Even with the resources that we have at our disposal, these are simulations that are just simply too expensive. And so one of the things that we do is to try to accelerate the process. And I'm just going to show you a very quick idea, because it connects very nicely with the project that we have in terms of complexity, multiphase complexity. So the basic idea is that if, and you're all familiar, I'm sure, with the idea of statistics computed to realization, to Monte Carlo sampling. In this case, the key problem is that the cost of running an ensemble is proportional to the number of members, the number of simulations, and the accuracy is inversely proportional to that number. And so you clearly you have a limited budget, a limited possibility of running simulations. So n will be small, but with n small, then the accuracy is very small as well. The error will be large. And so one idea is to actually, the simplest way to accelerate is through control variables, which is an idea that uses a combination of actual simulations and a cheap estimate. In this case, if we are able to predict the quantity of interest we care about in a cheap way, and P will be that prediction, we can actually prove that in this case, the error that we're introducing through estimating the quantity of interest is actually proportional to the exact same quantity as before. So the true variance of the estimate and the number of simulations that you're running. But there is a correction factor, the 1 minus rho square, where rho square is actually related or proportional to the correlation between Q and P. So if you're able to find a P, so a cheap quantity that actually correlates well with Q, then we can end up with a much more accurate estimate of the quantity of interest we care about, of the statistics of that quantity of interest, with just running very few simulations. So that's the basic idea. But the question is how you actually build P. What is a good, in a sense, a good surrogate for our quantity of interest? Now, it turns out that in simulations has been fairly well established that you can use coarse grid estimates. So suppose you're running a simulation, if you just run it on a coarse grid, typically that is a good representation of a control variant for the high fidelity for the fine grid simulation, with obviously some caveats, but this is typically a good, a quick surrogate build. Now, it turns out for a multiphase simulation, coarsening is actually not a simple exercise. You can coarsen in many ways. You can coarsen the turbulence calculation, so you can reduce the spatial temporal discretization. Similarly for radiation, you can reduce the number of particles. You can switch on and off certain coupling terms, or you can simply use different assumptions. So for example, for radiation, you can use a diffuse assumption and perform that radiation estimate in a very cheaply compared to, say, a discrete ordinary kind of simulation. So that the problem then becomes how to pick one of them. And just to give you an idea, just a visual picture of how different this coarsening estimate might look like. These are 5 of them. I call them low fidelity here. They are much cheaper estimate of the high fidelity. And in this case, I'm just showing you a snapshot that illustrates how, for example, certain assumption like LF4 is very different, at least intuitively, from the original picture there. Now, the question is that actually useful or not? And that becomes now a completely different question of how to design a surrogate in this particular setting. Just to give you an idea, we have, for this particular simulation, more than 1,000 of actual options to build coarse calculations. And it turns out these cost calculation can be extremely different in terms of costs and in terms of capabilities. But the question is, how a priori can you actually do it? It turns out that one process that we've used that is actually fairly effective is to build them as a sort of an optimization strategy, or build them through an optimization strategy. So the picture I'm showing you here is actually a comparison between the high fidelity calculation. In this case, the quantity of interest is the heat transfer or proportional to the heat transfer. And I'm showing you here 4 categories of models. They're sort of limited by these lines here. And these categories are basically different by an order of magnitude in cost. So moving from left to right, we are sort of decreasing the cost all the way to 10 to the minus 4 of the original cost. So you can imagine you can run 10,000 of this coarse model comparing, compared to in the same time it takes to run one calculation of the high fidelity. And it turns out that if you actually look at this calculation, there is a group of the simulation that gives you a very reasonable comparison. In this case, I'm looking at about 20 calculations run with different parameters. So the comparison is not one-to-one, it's a distributional comparison. So there are obviously good choices along this range. And the way this was built was not simply randomly picking, say, 30 low fidelity cases. The way this was done was to build first the case that decreases only 1 order of magnitude, and pick the calculation that actually are able to be closer to this, and then pick only one of these coarse simulation, and then reduce the cost by a further order of magnitude. So the idea is that the process is actually sequential and allows you to build now a family of models that allows you to go from extremely low cost to the extremely high accuracy in a way that is controlled in a sense. And the important thing is that intuitively these calculations are not easy to identify. And so in fact, we actually have done interesting comparison with choices of different models that would be sort of physically motivated, or at least driven more by the experience of the team members that were actually running the simulation. It turns out the choices that the optimization algorithm did for us were actually quite different from the one that individuals know. But anyway, the bottom line is that at the end of the day, you end up with the ability to run multiple calculations at low fidelity, but still build confidence interval for the high fidelity calculation. And this is sort of the end results of the uncertainty quantification effort. But just to give you sort of a sense of why we're doing this, confidence intervals are valuable and useful to sort of build a comparison. But the other advantage of doing this sort of ensemble of simulation is that it sort of tells you which one of the input uncertainty are actually dominant in terms of the variability of the output, so that you can actually reorient your resources and focus on elements and aspects of the problem that perhaps demand more evidence and more information, so that you can reduce the input uncertainty in those particular settings. And it turns out if you do this, and this is a bar chart that explains or describes the relative importance of the various input uncertainties on the quantity of interest of the transfer at the end. And you can see that the spatial distribution of the radiation source turns out to be the dominant source of uncertainty in the problem itself. And so the next step in the process, obviously the project is finished, but is to try to get a better handle on what is the actual input distribution, not in terms of frequency or in terms of intensity, but really in terms of spatial distribution, because it has really such an important effect on the problem. A relatively quick discussion, but I wanted to mention computing because it is a critical element of this project. In all projects that we run since actually the very beginning with the channel flow, the connection to architecture, hardware, and also the connection to computer scientists has been very valuable and very critical to actually proceed in this setting. Just to sort of explain, at least in principle, what is that we've been doing. the key element is that achieving sort of compute performance, and this plot, I'm sure you're familiar with it, the top 500 supercomputer list. Achieving sort of performance on the system is complex, not just because these are massive scale systems, but also because the paradigm of computing has changed substantially. So when I started as a computational scientist, computing was all about reducing the amount of flops or the amount of floating point operations that you do in your calculation. So storing quantities or memorizing sort of intermediate results to use them afterwards is sort of a key advancement in sort of reducing, compute. It turns out nowadays compute is basically free. So we are at the scale where the most problematic issue is actually moving data from one memory location to the actual compute resources. And so the problem is that the paradigm has completely changed. And if I sort of want to explain this in graphically as an Italian, I would say that what has really changed, and these examples here are intended to give you the idea that if you jump on a 500, the car on the left, it's very likely that you will have full confidence in pushing it to the limit, and you will get the performance that you can achieve on that system without any trouble. I already, sort of guarantee you that if you jump on the car in the middle, I haven't, but if I would, I wouldn't be as confident, or perhaps it wouldn't be as straightforward. And especially I would be very concerned about, breaking something or perhaps, not really being able to use it properly. But I can certainly guarantee you that if you jump on the car on the right here, so the Formula One car, there is no way that this will even start, right? So although the performance are there, it's not really easy to obtain them. So what has really changed in terms of this paradigm, and to, again, to build an intuition of this, is really the user interface. What you need to know to get performance out of an exaflop machine is actually extremely more advanced than what you needed on your laptop these days, right? So the challenge is really how to interface with this system, and part of the challenge has to do with the architecture. So the fact that there are very, very complex memory hierarchies, there are different type of chips and so on, but also the software abstraction. You need to know quite a bit about different compute models. Obviously you have C++ or Fortran, you have CUDA, you have other programming models, but also all these other elements that are required to actually get the system to work as a unit. So message passing, or passing information between different cabinets and so on and so forth. Now, it turns out it's very, very difficult to expose all these elements into a programming model. But this is exactly what we have been doing at Stanford within the Legion programming model and within the Legion project, which is in collaboration with our computer scientists. So I don't have time to go in a lot of details of this, but the key element I want to mention, let me skip this, is that we basically write C++ code in this project. There is no explicit data layout. The data layout of our information, so we never define an array, just to give you an idea. And this is all sort of managed and organized directly by the programming model and the runtime. We don't have explicit data communication. The data communication is defined once you have a task that requires some information, then the data or the programming model knows that the data have to arrive to that task whenever the task is going to be ready to sort of operate on a compute unit. And also there is no explicit hardware dependency. So we write basically code in C++. Is a sort of a modified version, or there are sort of multiple libraries in C++ that we use, but it's C++ code. And once it's executed, then the necessary code is generated for, say, GPUs or CPU or whatever type of hardware we have. And so that has sort of changed dramatically the way we operate. We write basically a single code that can run on CPU and GPU with very, very good performance. These are just examples on running our system now on very large scale compute, both on CPU on the left and GPU on the right. And again, with a code that doesn't really have CUDA explicitly sort of interlaid within within the software itself. Now, one of the things that is interesting about these sort of project and the idea that we have sort of these monolithic single code that we can run on different hardware is that one of the things we can do is that we can run low fidelity simulations, so these coarse simulations along the high fidelity simulation on the same nodes. So this is an example that shows what happens if we have an high fidelity calculation running on GPU, and most of the calculation ignores basically the CPUs, and the CPUs sit idle. In this case, on a machine like Summit, you have still about 90% or 10% of compute that is actually available because the CPUs are not really being used on a single node. And it turns out with this computational framework, we can actually run simultaneously one high fidelity simulation on GPU and up to about 12 low fidelity simulations on CPUs of the same node. And in this case, it means that our low fidelity simulations are essentially free, right? We can get an ensemble of low fidelity and high fidelity basically just by running a few high fidelity calculations. Now, to finish, I just want to say, okay, we have sort of run this project. We have been able to build estimate now of, say, heat transfer in a way that gives us confidence. Now, this would not be very exciting or very satisfactory from an engineering context, because the question is if we have sort of learned anything about the system itself. And it turns out that by doing some analysis of the results that we collected, we were able to actually build a very, very simple relationship that allows us to correlate performance and efficiency of the system directly to a non-dimensional number. So we were able to identify a non-dimensional number through a data-driven approach that basically controls the efficiency of the system. Now, the collapse of this data is not perfect, it's far from perfect. There is actually a secondary effect that is also present in this problem, but at least it gives us some really nice and easy design insights that tells us sort of some expected dependency. For example, epsilon in this case is the absorption, the particle absorption for the system. So we need sort of to account for that. AR in this case is the aspect ratio of the system, so the geometry of the window basically of where the heat transfer is being injected. The RE lambda is clearly a measure of the turbulence in the system. And R, in this case, is a measure of the effectiveness of the source, the radiation source, the transfer of the energy from the radiation source to the convective fluid is a measure. It's kind of a dumb-colored number in some sense for combustion or for reacting systems. So this is a nice sort of summary that gives a design insight that might be used for the future in the sense in the system. So I know that I'm running out of time. So basically, maybe I'll skip the last part, which is the project that we're working on right now, and just go to conclusion at this point. So let me just say that I give you some highlights, not obviously a lot of details of these projects, but there are a number of lessons learned, and I'll leave that as a comment for later. So the idea of multiphase simulation, the part that has to do with sort of embracing computing at a different scale and quantification of uncertainties are clearly sort of the main themes of these projects and sort of what we are very excited about. I just want to acknowledge obviously the Department of Energy and the ASCI program for the support over these many years. And there is a tremendous team behind this project. This is actually a team working on the current project that involves, graduate student postdocs and a number of faculty, not just at Stanford, but at Boulder and at Purdue in this particular example. And with that, I'll finish and thank you for your attention.
Thanks a lot, Gianluca. So now we have time for questions. So if you have a question, you can put the question in the chat. If I already see that there is one there, and then I can read the question out loud, or also raise your hand. So the first question is, as we know, the AI topic is hot these days. So how will AI affect this computing and simulation? So what are your thoughts on that?
I agree. It's clearly a new component. We are actually in the new project. We do have quite a bit of data science related activities. I prefer to use data science as a term rather than AI, at least in this particular setting. The way we are using is twofold. On one end, we are trying to build better models for the physical phenomena that we're not representing directly. So you can think of, subgrid models or perhaps models that are related to particular aspects of the physics that would be too difficult or too hard to represent directly through solutions of PDEs. So that's one area. The other, which is actually even more exciting and interesting, is to use a data science model or data-driven model as surrogates for our fidelity simulations. And so they become part of the uncertainty quantification framework that we're building. And we are doing actually quite a bit of work these days on that. So these two are, at least for the project that we're running right now, very active area of research. And I can imagine that there are other opportunities, but at least these are directly relevant to it.
Okay, good. So if you have a question, you have to raise your hand so we can unmute you. So yes, or you can still write that on the chat. In the meantime, so I have another question for you, Gianluca, is more about what are your thoughts on all the experience of this year. So you mentioned three components. There are numerical methods, there are simulations, literally like high performance computing, there's some coding involved, and then there are physics. So what is usually the main bottleneck for really making progress? Is there a particular bottleneck, or they all three go together, or is always in your experience clear that, for example, I don't know, maybe the numerical methods are really lagging behind, or what are your thoughts on that?
Yeah, that's a great question. I think at different times in this project, you see sort of that one of these elements emerges as a critical element. I would say it's difficult to sort of say that there is one that always dominates, but certainly at the inception, the physics is what drives, right? You're trying to build a picture of the system. And so physical understanding and physical modeling is sort of critical at that stage. Then simulations and high performance computing become sort of the key bottleneck in terms of sort of building up all the infrastructure that you need. But then what's interesting is that at that point, it's kind of difficult to sort of go back and forth and try to improve models, because unless you have a real evidence that there is one element that is dominating, one limitation that is dominating over the others, you just cannot really make clear decision. And so at that point, uncertainty quantification becomes critical to sort of drive the next step of the process. And so I think it's a really nice combination of how all these elements become important at different times in the project.
Good. So we have a question from Andrea. So yes, please unmute yourself and ask the question.
Yeah, thank you. Yeah, good morning, Professor. Thanks for your very interesting talk. I have a quick question on the project you are working on that you didn't have a lot of time to discuss today, that is the laser-induced cryogenic turbulent combustion. I was wondering if your group already has some publications out for conferences or journal paper, and in particular, I would like to know what is the way you are incorporating data science and machine learning in the laser-induced laser plasma interaction framework. Thank you.
Thank you for your question. Yes, we do have several publications already, and if you email me afterwards, I'll be happy to share some of those. They're conferences and whatnot. Now, on the data science side, though, I think we are still a little bit behind. I think the primary or the most advanced is to model. In our case, the fuel is coming as a liquid fuel. So obviously there is a process of breakup and evaporation that we need to capture. So we're using data science and specifically machine learning to build models of that process in our simulations that will be then incorporated into sort of the general simulation framework. So that's one area that has received quite a bit of attention. And the other, as I mentioned, is the idea of using machine learning as a low fidelity alternative to, say, coarsening for doing uncertainty quantification. And there we're using typically variational autoencoders, and there is there are several elements that have already been published, but that's a very, very active area of research at this point.
Yeah, thank you.
Okay, good. Do we have maybe time for one more questions, or maybe two, depending on if anybody has questions? If not, I also have another question for Gianluca. It's still very high level, and it's about what is your opinion? So you mentioned about the center, and the center actually has a very nice budget, and there's a lot of people working on this. So, but how do you think that this can compete right now with industry? And I'll tell you one example. For example, people from the example of nowadays, Microsoft decided to put $1 billion in creating a ChatGPT, and then they created this system. Just training ChatGPT was like $100 million. So is it, I mean, what is the role in academia now? Now, if people from industry, they really want to solve a problem, isn't it that they will just put enough money, especially these data-driven kind of approaches? Isn't that that they will just nail it and academia cannot compete? Or what do you think is the role of academia in these cases?
I think that's a great question. I really don't know how to sort of articulate a role in that setting for academia, because I mean, in a sense, even sort of the overall idea of research and trying to sort of build, foundation and then sort of, insights and so on and so forth, it's sort of not really part of that paradigm. It's really just, very, very driven by a specific goal, collecting information, run the algorithms. It seems to me, very orthogonal to what we typically try to do in academia, which again is sort of more of a step-to-step approach with trying to build insights and so on. I would say my sense is that one of the things we can do though is that we can incorporate some of the elements that are more typically used in data-driven models for taking advantage of some of the limitations that our systems have, right? I mean, again, Microsoft won't be interested in, very much in physical systems. And on the other hand, physical systems have constraints and difficulties that are actually not matching very well with some of the, current settings of something like ChatGPT, right? There are, some constraints, some reliability, some safety consideration and so on that are not just, they're not just hypothetical, right? Privacy and so on. These are real, very, very real constraints that the physical system need to have to survive, right? In terms of if you're designing a with energy device or something like that, right? There are, again, sort of elements of that I don't think it's clear that the same methodology that is used for some of the most, exciting applications right now in machine learning would be really applicable. And so, perhaps academia can help there, sort of understanding how to bridge. We can do it. We know very well how to do it with sort of conventional simulation, but it's just too expensive, right? And so I think, moving in a way that allows us to merge perhaps these two paradigms in a way that is effective in terms of, resource utilization, but also, include some of those constraints. I think it's perhaps the right role for us.
Yeah, I also want to believe that we play an important role in academia, and I also like to think about that. I think that we, because we are kind of the same field, we are not still affected by this, but I can already tell some colleagues from CS that they have these mixed feelings now of what is my role. I think that people that we are not more focused, like physics is a very strong component of what we do. We are not affected by this yet. But the question for my other colleagues from CS is that they're starting to question, what am I trying to do here? I mean, if I don't have enough resources to compete with these people.
Yeah, no, that I agree. I think direct competition, I think is it's difficult to imagine a scenario where you are in, that you can actually compete. But, on the other hand, I like to think of, the scientific method and the fact that, that there are approaches where you start from theory and then you build your prediction, right? And there are approaches where you start from data and you build your prediction. Right? These two are sort of two different sides of the coin that is scientific method. And there has to be a way to actually take advantage of both, rather than ignoring completely one side and now just do everything, on a data-driven type setting. So I think that the question is really finding their balance.
Yeah. Okay, I think that we are almost perfect with time. So I want to thank you again. I was very happy to have the chance to see you virtually. Hopefully, I'll see you in person sooner than later.
Yes, absolutely. Well, thank you for having me. It was
yeah, of course. Take care. And thanks to everyone for joining. Bye.
Thank you.